Fundamentals of Smart Grid under MIT. Today we'll be talking about design of smart grid and practical smart grid case studies. Why I made 1 and 2? Because I'll be talking about two different type of power hardware in loop simulation and control hardware in loop simulation. So today we'll be focusing on both CHIL and PHIL. So my idea of today's lecture is to help you out. If you wish to develop a smart grid laboratory and wish to carry out some CHIL or PHIL experimentation, then how do you do it? That's the question. So first of all, uh, this is what actually my lab in one corner looks like, where you are not able to see most of the component, but this is one angle actually. So this is basically a wonderful setup. What are there actually? If you see, there are two racks in the left-hand side. Hope I'm audible loud and clear. Please say yes in the message if it is so. And you could see that there are two racks. So the left one is my AC microgrid uh, setup. Okay. And the small one corner, but right. Corner left is the AC microgrid setup, and corner right is the DC microgrid setup. Okay. And then both together become AC-DC hybrid microgrid. And then they are connected to the RTDS as a simulator through the amplifier, which is lying in the center. Okay. If you see the other part, which is not visible here, you will find next to the AC microgrid, you will find another amplifier of larger size, so that you can do PHIL for the AC microgrid, you can do PHIL for the DC microgrid, you can do PHIL for the AC-DC microgrid. So that is the idea how the lab has been expanded. And similar to RTDS, the left-hand corner after the amplifier, you will find the Opal RT rack. So now what you can do, you can do first, you can do PHIL for DC microgrid, you can do PHIL for AC microgrid, you can do PHIL for AC-DC microgrid, you can do PHIL for AC-DC hybrid microgrid using RTDS, you can do PHIL AC-DC hybrid microgrid using Opal RT. So that means whole world is just with you. Whatever you want, you do it. All right. So that is what, and then the story doesn't end there. So after the Opal RT, you will have a grid emulator. So that means the grid which has been made synthetic. You see the glass door. Glass door behind, actually, we have a small substation. Okay, the lab also has a small substation at my grid, which is just behind the lab. That's what I partitioned. Okay, and then adjacent to the substation, we have the battery rack. We had a huge battery, which is there, which is not visible in the diagram, but we have a battery. And then adjacent to that, we have a diesel generator. And adjacent to that, we have a electric vehicle charging facility, a charger, EV charger. Okay. And then adjacent to that, we have the BMS setup. So this is what all about the laboratory. So you have a complete microgrid, and then you see there is a exhaust fan, no? So just top of that, we have the roof. This is in the first floor. And then top of that, we have PV panels. We have huge PV panel, but a reasonably 1 kilowatt PV panel physical, which has been connected there. And then if you peep in the window, you will find a huge battery in the right side of the lawn, which is of close to 272 kilowatt hour battery, which is lying outside. And adjacent to that, we will find another larger substation, because this substation is 400 three-phase substation, and that is actually 11 kV substation next to the battery. So if you see, the whole world is within you, and whatever you want to do, you can just do it. Okay. So you have battery, you have EV charger, you have PV, you have emulators, you have simulators, you have DC grids, you have AC grids, you have amplifiers, you have grids, you have almost everything. Okay. So anyway, it has happened with over a period of time.
Substation required for lab experiments or
Yeah, yeah.
department?
No, we have for this lab only.
Lab only.
This lab only. This substation is for the lab only. So that we do independently. Department, they have a 11 kV substation which is going there, but this substation is for this lab only actually. All right. So there is a small story behind. I don't have time to tell. Otherwise, I would have told because this lab has actually started with another lab actually, which is very popularly known as. I have been made PI of a project which is of 100 crores grant. I was not the original PI. Professor Jayadar Sarma happened to be my group leader. He was the PI. But before he retired, actually, he has handed over that lab to me and made me PI also. So, so the responsibility is to develop, simulation software like replica of MATLAB. That was the work. So, no, it is algorithms. All algorithms, free source. Today, everything AI, everything has happened, but that time actually we were creating a open source actually free material for poor child of this country, those who do not have actually access to original MATLABs. Okay, that was the vision for the government actually, might be sponsored if I'm correct. So this was the place actually, we had a substation, we have more than 30 computers, so it was working, but later on it got over. So then we started doing this business, okay? So fine, fantastic. So let us move to the facilities which are available to have a glance, okay? So if you wish to have some facilities, you can create your own. So we have RTDS of 6 rack, PB5 processors, and we have GTAO, GTDO, GTDI, and GTI cards available. And possibly it is possible to simulate close to 432 nodes. How many nodes? 432 nodes, okay? But this is not enough. This is very small. Even it cannot simulate a true MNIT campus distribution system. Because if I take everything is a node, then you will have thousands of nodes, no? So these are actually master nodes. One substation will be like one node, okay? So then we have a power amplifier. So this was a really interesting device. But this, what we are mentioning is one power amplifier, which is of actually 5 kVA continuous, means you can connect to a hardware device of 5 kVA and you can operate continuously. And if you do it for short time, maybe for a couple of minutes, then you can go with 10 kVA. And if you want only for a few minutes, even less than that, then you can go up to maximum 40 kVA. There is a spike, it will tolerate up to 40 kVA. Now support power hardware in loop, which is PHIL, and high accuracy voltage and current measurement for PHIL possible. Support AC microgrid up to 270 voltage RMS in each phase, and just when DC microgrid up to 400 volt DC, and it can operate up to 4 quadrants, and zero lead, zero lag, and unity power factor operation is also possible. Uh, okay, there's some issue. Yes, okay, good. Yeah. So then we move to hardware facility in the lab. What are the hardware facilities we do have? So we have actually PV emulators, and PV emulators are of different types. But actually we prefer to have actually two PV emulators because the idea was to have at least a 5 kilowatt capacity to start with. So we have 5 kilowatt of actually PV, 1 kilowatt which is coming real, and 4 kilowatt which is coming through emulator. Then we have included actually shading effects, real world weather simulation, static and dynamic MPPT, they're all inbuilt in that emulator. So this is a good quality emulator. So probably you all can also get into emulator which has these features. Now moving to wind emulator, you can see the setup. So this setup actually being built within the lab actually. So we have a DC motor driven DFIG, and the rating is close to 2.2 kilowatt. And we have actually two simulators, wind. One is induction based, the other is synchronous based. But the synchronous base is just next to this, so which is not visible at that time. And real wind simulation is possible, and MPPT tracking is also inbuilt. We have a rooftop of 1 kilowatt, as I mentioned. And then very interesting part, actually, we thought when you are simulating a smart grid, either it is DC or AC, it must have a diesel generator, because in this country, DG is a very common, no, diesel generator. So if you do any study without taking diesel generator, means somewhere actually we are not bringing clarity to Indian smart grids. Okay, so I forcefully, introduced a diesel generator of 3 kVA capacity. Okay, so now tell me what are the sources now? 5 kilowatt of actually PV, and then 2.2 kilowatt of wind, so 7.2, and then this is 3. So 10.2 is my generation now. Okay, and then we are bringing to storage. Okay, storage, let us say best battery of actually 60 ampere hours, ultra capacitor of 58 farad, and the loads actually we had 1.5 uh, megawatt, sorry, 1.5 kilowatt of actually load. But actually, instead of making physical loads in the laboratory, so we have gone for a smart load setup where actually all combination of constant power, constant impedance, constant current loads can be implemented and realizable. Okay. DC, AC both. Everything is possible. Okay. So I think this is a 3 numbers of programmable electronic load to simulate all type of loads, either it is DC or AC or any type is possible up to 1.5 kilowatt. Then we have different type of converters, and then we move to hardware in loop simulation. So it is popularly known as HIL. So this is a very, very important concept. I request all of you to please have attention to this area, and because almost all of us are reading for the first time, okay, hardware in loop simulation. So hardware in loop simulation, as I told you, there are two types. One is control HIL, and the second one is actually power HIL. Control HIL is known as CHIL, popularly known as, and power HIL is known as actually PHIL. So what is HIL? So in hardware in loop simulation, hardware devices are interfaced to a real-time simulator which contains rest of the model necessary to test the device operation. Means I have a microgrid. In that microgrid, I am interested to test the performance of a battery, let us assume. So I will have the whole microgrid being planted in my simulator, either OpenRT or RTDS or any platform, they will have everything. So what device I have, actually physical device which is lying outside is my battery in this case. So in hardware in loop simulation, the hardware word is coming because of that device. In loop simulation, because it is getting through the simulator. Hardware device are interfaced to a real-time simulator, which is a system, or my hardware setup could be the rack that you have seen is a DC microgrid. So DC microgrid is my physical device, and MNIT Jaipur or IIT Roorkee distribution system become a software planted within the simulator, and the electrical engineering department bus, which is coming out of the simulator, and the DC microgrid is physically present, which contains rest of the model necessary to test the device operation. I want to know how my physical hardware device is going to operate in real time. So tomorrow, if I put a battery in a real distribution system, how it is going to perform in real time can be experimented in the laboratory through hardware in loop simulation experimentation. So HIL simulations offer a cost-effective and safe method to test physical devices under real-time operation conditions. So you are not really operating real time; it is as close as good as real time only. Now, HIL simulations can be open loop, where signals are sent from real-time simulation to the device, or most commonly we do closed loop, where the response of the device is fed back to the RTS. Means the simulator will give some response, you do it, again you revert back to the system to see how it is responsive. So when I say the analog signal, it will go to the device, means it will go through a amplifier. Okay, so that amplifier is required, which is a bridge between your hardware device and the simulator. Okay, are you getting my point? So now there are two types of simulations. Let's see what is hardware in loop simulation experimentation. We'll focus on actually CHIL first. So in CHIL, physical control or protection relay devices are interfaced with the RTS and exchange digital and or analog signals. In CHIL, physical control or protection relay devices are interfaced with the real-time simulator and exchange digital and or analog signals. So in most CHL applications, the signals can be exchanged at low voltage level, that is plus or minus 10 volt, because the simulator is alternating device, okay? And allowing a straightforward interface with RTDS using digital analog DA and analog digital converters. So you see the below diagram, you have a RTS, real-time simulator, and the real-time simulator gives signal to digital to analog converter. Am I right? And then that analog signal will be amplified through an amplifier and then given to the device. So device performs and then give a closed loop signal to the analog to digital and revert back to the simulator. So what happens? The interface between real-time simulator and the device is possible only for actually analog to the device, whatever the analog equivalent you get, that need to be amplified to the device level. Now, yeah.
In this case, the maximum rating of device will be based upon amplifier, whatever
Yeah, certainly. No, you cannot. Now, similarly, when you go to the power hardware in loop simulation, it is almost the same thing with a minor change actually. So here what we're doing, we have a real-time simulation and we do the scaling, standard one, and then we have digital to analog conversions, and then you have an amplifier, then it is going to the device level, and then the feedback, which is instead of coming to A to D directly, it is coming through your voltage and current sensors, and then you get that signal, and then you filter little bit actually, and then give to the simulator. All right. Now moving to the next. So with today, the very interesting part, we have done many experimentations on CHIL and PHIL. And dear gentlemen, it is very interesting whenever you try to attempt, to solve any problem related to CHIL or PHIL, you have to be extremely careful because we burned and we celebrated many Diwalis in the laboratory also before we come to this stage. Okay, so you have to be extremely careful. So control hardware in loop CHIL experimentation, we have experimented two case studies. The first one is going to be power flow control strategies, and second one is going to be isolated DC microgrid operation. So these are the two experimentation we used as a HIL, we call HIL experimentation, but they are control hardware in loop simulation. And the other two is actually power hardware in loop simulation. I'll be talking about DC microgrid integration to IIT Roorkee network. Okay, so this is our USP actually. So we integrated DC microgrid to a real distribution system, which is in a megawatt scale actually. All right, so that interfacing was really challenging, and we'll show you how the PHL happened. And then coordinated voltage control of IEEE 33 bus system that we discussed in the past, where we have taken a 33 bus system, we connected a DC microgrid, we connected a OLTC, we have connected a STATCOM, and we connected a DFIG in the bus number 522 22 and
11.
2022. 5,
think
20,
5
22.
5 and 22 is confirmed.
Yeah. So the other one actually,
12.
can we ask a quiz question to our students? What are the buses where, so we had connected, tell me anyone, what are the buses we used in the previous class for integrating wind plant, STATCOMs, DC microgrid and OLTC. OLTC is connected to fifth bus, am I right? No, DC microgrid, is it? Okay. So all of us have forgotten. Anyway, okay, 1 2022 or 1 5 22. 1 5 22. Okay, so bus number 1. I think somebody is saying 5 18 and 22. Okay, no problem. I think it's an interesting thing. All of you, please have a check, okay? And rest assured. I think bus number 1 to nahi tha. It was something different. So I think probably 5 18 22 maybe right. I don't know. Actually, let us have a look, okay? Okay. So today we'll be talking about that same example for our PHL. We'll go to the next slide. So we'll be talking about which problem we'll be talking about? CHL for power flow control strategies. So this problem actually, all of you please concentrate that this problem actually we have already solved using RTDS. We got all the simulation characteristic using the control strategy using RTDS. But we have not used any power hardware in loop simulation because these devices were never been connected to RTDS in a physical mode.
1522.
1522, very good. So thank you. So Salendra was correct there. Huh? Okay, good. So now, if it is so, then power flow control strategy, what we have simulated, we like to do it actually again with the CHIL experimentation. Okay. So this is what all the scenarios are. But now the control strategy is not in simulated mode, but it is in physical mode. And these are the simulation you'll be getting it now. Now the question here, what is the interesting part compared to the previous one and this one? You all of you please have a look. If you zoom those diagrams, all of you please have a look. I mean, these pink line, these blue lines, they all were actually perfectly smooth. All these signals in the RTDS simulator, it was almost considered to be a perfect one. Okay, they were very smooth, but they're all physical mode. Okay, so in physical mode, actually, you could see almost everything is giving you bit of noise, bit of harmonics, it's everything. So you could see the input currents, grid parameters, DC bus voltage, everything they are being properly measured and simulated. So what I am saying, whatever analysis we have done using RTDS in the previous chapters, the same experimentation we can do using a PHIL experimentation. And this will give you a different scenario. So this is for peak hours, and then you will have for off-peak hour, and then you will have for isolated one, okay? So this is for your off-peak simulations, isn't it? And then experimental setup used for peak mode, off-peak mode, and finally for isolated mode. So could you see the noise level? Are you able to see? Huh? So these are actually true hardware results, okay, using your CHL experimentations. So everything, I mean, nothing is free actually, you see. This is how it looks really. Am I right? But in the simulation, it will look almost perfect. All right. So can we move forward? Yes. So I think we'll move to the second case study where actually we connected everything we learned actually in conventional RTDS simulation, but not CHIL or PHIL. So interconnection of two local DC microgrids. Here, the energy exchange or the current flow between two buses that can be seen through your CHL experimentation. So here what we are doing, bidirectional power transfer between two, DC microgrid are being actually realized. But you remember there we have considered in case of simulation, one is of 48 volt and the other is 360. 360 or 380. 380, okay. So 380 volt and 48 volt, okay. But here we realize actually playing with 380 volt DC in a PHIL actually a bit risky. So for the safer reason, we have gone for actually 100 volt and 48 because we are supposed to demonstrate the challenges with two different microgrids interconnected, okay. So we have considered lowered down 380 to 100 volts and all the modes are studied with respect to both the DC microgrids. Control algorithm is effective and efficient in transferring the power between DC microgrids. Reliability of DC microgrid is increased without additional storage capacity. Now, this is going to be the third one, third setup actually. Okay, the case study 3. But before that, I like to show you, perhaps actually this one actually, I like to take little bit of credit by saying that this idea is not belongs to any students as of now. What I'm going to say, show you here, the PHL experimental setup actually. So fortunately, this happened to be my dream child. And I saw a dream and then I thought I will implement it. And this has been done. So what dream I had actually, um, you have microgrids and I say ki there could be millions of microgrid in this country or in the world. And it is impossible to simulate all the microgrids simultaneously. But only you can test one microgrid at a time. So the idea was, can I not simulate the whole country that is happening today? Power grid is simulating the whole country, okay? So I'll have the whole country network and that I will burn in the RTDS, only the racks will change. Instead of 6 rack, you need 600 rack. The whole country can be burned, grid, and one particular bus which is at Rishikesh, which is a 400 volt, 400 kV bus. There is one bus actually which is a 400 kV bus in Rishikesh. That I will actually simulate and then bring back to 230 kV in Haridwar and then 33 kV in Roorkee and 11 kV of the campus and then electrical engineering department microgrid will be a physical one. Rest all will be. So IIT Roorkee microgrid will be connected to a 400 kV bus of India and the system will be simulated. So that is what actually I have attempted. But fortunately or unfortunately, this work has never been published. This is still a suspense. Okay, I will tell you because we spend nights and nights together, but it's still a problem. And wonderful, this is another PhD problem is still awaiting for anyone who can like to do, because the idea is already there, but I could not complete it. We have tried actually. What we have done, we have taken IIT Roorkee distribution system and integrated the microgrid. So we were successful up to that point, but we could not burn the complete Indian grid because of limitation of RTDS. Okay. But today I have been told that Opal is coming out with very reasonable cost with big capacity of simulating many buses. So probably with the same cost, we spend around 8 CR at that time. Okay. So if you spend 8 CR on Opal today, I have been told that it can build more capability compared to RTDSs. Anyway, this is a computation. So you all please have a look. So what I have done, if I zoom, so all of you please concentrate. See the idea actually, forget about whether you are able to do it or not. So हमने क्या किया actually, we have taken the complete, slowly I am zooming it, all of you please have a look. So this is the diagram. So this is my all India network. And I can simulate in MATLAB, I can do in RTDS, wherever I want, I can simulate the all India grid. Because I want to do PHL for all India grid, means a microgrid of IIT Roorkee. And if there are millions of microgrids similar to IIT Roorkee in the country, MNIT will be one, right? Rajasthan University will be one, SMS will be one, IIT Roorkee will be another one, for an example. How all the microgrids will impact the national peak and national off peak. Then only you can do it, na? When I'm connecting a grid, having a microgrid, I discharge my battery, I say there was a peak, so my battery helped. That is true. But national peak reduction, to reduce the national peak, all the microgrid in the country must act simultaneously. सबके पास सिग्नल चाहिए जाना चाहिए कि we have already reached the peak. Let us all discharge our batteries. Then the peak can be handled. So this is what the attempt. So probably a long back, actually, 15 years back, I dreamed a problem. I never thought that this is unsolvable. It is solvable. The idea is clear, but how we are going to do is question. So then, in this that box you see, there is a small box. No, so this is where actually we live. Uttarakhand comes to that region. So our lab falls on. These are all 400 kV buses of the country. They're all so our 400 kV bus actually falls there. So this is what you have seen, the zoomed one, and you see zoomed one look like this, left hand side. So there, introduction of DC microgrid at Uttarakhand. Very different dream, no? I enjoy it when you cannot sleep if you start dreaming like this. So this is what actually we connected a microgrid in the Uttarakhand substation of 400 kV, and then we want to say what is going to happen. And this is the first time. And then second, very important, if you take each and every bus of the network, all of you please try to understand when you go for.
So,
Okay. So what I wanted to highlight was the network, which is so big, none of us actually can simulate in any platform. So to simulate a large network, we need to reduce it to a reasonable size. We have to reduce to, what do you mean by reduction? Means if you have 1,000 bus, can I reduce it to 100 bus? How it can be reduced? Because let's say I have a device which can simulate 432 buses. I like to simulate my All India bus. So All India bus need to be reduced to 430, no. Then only I can simulate. So what I have done when I could not find a 100 rack simulator to simulate All India network, where Power Grid do have it, they have a big, very big size. For me, I thought of reducing the network to a size which is below 432, so that with my given facility, I will be able to simulate the all India grid. So that is what actually the problem now changed from a normal problem to a reduced network problem. So we spent almost a year, probably that time, if I'm correct, I used to travel all summer actually to North America. So I still remember actually day and night time. So my student used to work in the daytime and I used to work in the night time there actually. So that is how we used to work. So the right hand side is the true all India network. See the complexity. This is the original network. And we learned how to reduce a network and then we made like this. Then we made like this. So right hand side is original and we reduce to left hand side and then we connect and this has gone to the RTDS and then we connected microgrid. What a beautiful piece of work. Not even a single publication, no PhD thesis, but we have done it. कभी कोई कुछ मंदिर अधूरा रह जाता है ना, it is of that kind of work. I'm not finding any student who will dare to take it forward actually. It's a very interesting problem because you need facility, a lot of thought process. So the reduced network actually, which is already well established technique. So we have learned, we have understood, and then we have reduced. So what they do, they try to capture the features of the buses, which will give you the same load flow solutions, even having the original network. Let's say I have a network of 100 buses that I reduce to 50 buses. But if there is a specific line which is common to previous and this one, or there is a load current, that remains same in both the cases. Then only I can say I have reduced. So this we have done, and you could see the dot actually. So this network has been actually burned in the RTTS. Okay. And then finally, what we have done, the DC microgrid right side is belongs to the lab. This diagram actually is real actually. All right. This is real. So we have PV emulators, we have PV panels, we have batteries, we have supercapacitors. We had actually DC loads, and you all will be surprised. We had everything, even a heater you will find in my lab, which has been connected. सर्दी में बच्चे काम भी कर रहे थे, लोड भी चला रहे थे, isn't it? And then you have everything in place. I still remember we celebrated the day in the laboratory when our first DC microgrid charged my first mobile actually. That is how we celebrated. Mind blowing actually, it's not easy. DC microgrid to ho gaya, but it's working functional only when my mobile got charged. I still remember actually when it flashed, that charging symbol, no? So we all clapped and celebrated like we went to space actually. That kind of excitement. And I still remember the day. So you could see even there is a, could you see? Could you see there is a mobile phone? Ah. So we thought let us make it as a part of it because we bulb full sab to ho gaya tha, but when mobile got charged, we were actually very, very happy, and this is the real representative. Could you see? So this is my PHL setup in the laboratory of Admire Lab. So if you like to see what we are doing, you can do admire-lab@iitr.ac.in. You will find many information related to the lab. So case study 3. I think it is high time to acknowledge the lab scholars today. Can we open Admire that खोल सकते हैं? बच्चे को share कर सकते हैं? थोड़ा let them. In the meantime, I can have my. Please show that lab. Just. Admire-lab. Actually, मेरा था दे रहा हूँ सारे. Just, we like to acknowledge the scholars, those who have contributed significantly, because each and every lecture is more than 3 years of hard work. So we thought of actually acknowledging the scholars, those who really worked day and night. So go to the past scholar. No, no, no. Okay, go slowly. So just a minute, slowly. So these are the scholars a long back. My first scholar, second scholar, third scholar. Abdul is in Egypt as a professor. Simon is NIT Trichy professor and HOD. Come down, come down. नीचे आइए. Jacob is with VIT. Siddharth is with actually VSUT. Burla in Odisha as a professor and dean. JP Misra, the professor in actually NIT Slicher. Come down, come down. Rohit is actually NIT Jaipur. Niranjan Kumar is with NIT Jamshedpur. And Kanwardeep Singh is in Punjab. Come down, come down. And then we have Yadav ji, he's actually in Delhi College of Engineering as a professor. Shiv Kumar is in US. Nand Kishore is in Pune. Come down, come down. And Sanjeev is with actually NREL in US. Krishna Murari was a assistant professor in US, but now came back to IIT Billai. Then we have Gururaj with actually IIT Kanpur. Come down. Then we have Subhopal with IIT BHU. Rasmi with NIT Raulkela. Suresh Mangati with NREL, similar to Research Lab of Middle East, Abu Dhabi. Come down. Satabdi is with actually Shell. And Narendra Babu is with, they're into industry. I think she's in NL. I think Narendra Babu is with, it's interesting industry, Enphase. Nanda Babu is with Enphase, and Tripti is with also in Siemens actually. Yeah, Siemens, come down. And then we have Apruti with GE, Abhimanyu with Siemens, if I'm right. Come down, that's all. Okay, go to the current scholars. Let's see what they're doing like you. They're enjoying their life, huh? Current scholars. So these are past history. Now current scholars admire lab. We have Chaitanya, we have Nitin Upadhyay. Nitin Upadhyay is with ABB and Arpit is with GE. Their current scholars means before degree they got jobs. So they've submitted the thesis and all. Srikant with an industry. Subramanyam. Sobik is with GE intern. Come down and then slowly. Vinay is currently doing PhD. Vishwanath ji is one of my senior most research scholar I mentioned actually. He is 70 plus, 75 plus. He's doing his PhD. So we also learn. Okay. Veera is doing his PhD, come down. And Prashant, who submitted thesis, now going to university, Hong Kong actually. Krishna Reddy is also with GE. And Kasi got into a very excellent startup from US actually, but there is an Indian office in Punjab. So he's with the Chandigarh office working from home. Come down. And Garima, she also got a job. She'll be going very soon. Her synopsis got over. Anil Kumar Mathur, Ankur Singh, come down. And then Muhammad Raja Ali. Ankit Misra has gone to Hitachi. He has done his PhD after BTech. He has not completed, but I told him submit and go. And Arya is also submitting the PhD soon. Come down. And then we have Adyasa. She happened to be a PMRF fellow. The highest salary fellowships he's getting in the lab. He's working in real simulation, not hardware. Ali Muhammad, I told you, this gentleman is very good at hardware converter design. And Pragya is the very recent research scholar, the youngest scholar of the team. Okay. And then, probably next will be Vivek Saini aane wale isme. Good. So what the difference you have seen in past scholars and current scholars ke andar? Current scholars are very stressed and past scholars are very happy, isn't it? So I think this is what happens. And once you do the things and then things will be all right, you can open the NPTEL course. What are the courses we have developed using NPTEL end, yeah. So I think I request everyone to register for currently there are two courses. You see, Smart Grid, Basic to Advanced Technology. Anyway, we are learning now. Come down. And this is the course, Electrical Distribution System Analysis. I request all of you, Chandrasekhar, please register this course. This is a wonderful course. Even you too, Salendra, you all three, even including you. आप भी register करिए इस course. Very interesting course. Electrical Distribution System Analysis, because when you learn Smart Grid, you need to know a little bit about distribution systems. Otherwise, your Smart Grid is not complete. Because Smart Grid is always connected to. So if you like to broaden your idea, so Professor Ganesh Kumbar happened to be my colleague, but he passed away very suddenly in a very young age. And so for his remembrance, we thought this program should run. Okay. So you can also tell your students actually to make sure they should make this course successful. Come down. And then we have another, it is already done. Come down. This is a course with Gururaj already operating. Come down. And this is a very new course, which is talking about actually advanced distribution system analysis and operation, which is a modern distribution system. The previous distribution system analysis talks about distribution system classical, and this talks about more or less modern distribution systems. And this is also an interesting course which is happening. So these are the 5 courses available with us through NPTEL, but 2 courses are currently running. You can go back and then past, present, everything, lab facilities. Go to lab facilities, yeah. Because this course we are talking about lab facilities, okay? So, please. So slowly you can scroll. So if you like to read more about, because today in my lecture, I've given very basics. If you need to know more, actually, please go to the website and try to understand. So we have RTDS, come down slowly. Then we have a grid emulator, because these are all updated versions. That's what I wanted to show you. So we have a grid emulator. Then we have a power amplifier. And you see how many power amplifiers we have? Two. One is a 15 kVA capacity, the other is actually 22.5 kVA, means 37.5 kVA loading I can connect. Please come down. Then you have this wind emulator, complete setup. Then you have actually renewable source PV. Next, real-time simulation control actually here. Hardware platform, come down. Opel RT simulation. Next. Then we have actually advanced grid monitoring data analytics, all the advanced facilities. Okay, anytime any one of you feel that that like to use some of the facilities, you are most welcome. Go back, go back, go back. Main page. Anything else we like to see? Video. I think video you can go at least open it, open it. These are the videos actually we are coming back. So very quickly, you can just, we'll show at the end of our lecture, when you reach the 20th lecture, I will show you this video where I have taken the camera to each and every component of the building, whole campus, and just demonstrated actually how it is going to work. And this video, this work actually has won the IEEE Jury Award of the world. Only 3 people in the world will recognized every year. And this is one of them of the, so this is the hard work of what you see in 20 hours, won the best R&D lab and deployment in the world today. So that's my favorite. Anyway, with this note, we stop there. Come back, madam. You come to my presentation here. I'm very happy. Today the participant got increased. Slowly they become 55. Huh? I'm very happy. Normally the attendance falls down when the class comes to an end, but it is increasing from 25 to 55. So slowly they're realizing they missed something. Huh? Excellent. So now we are back and hope I'm audible. The reason of showing all these things to you is about just to motivate that the amount of hard work has gone to this presentation and the work that you are presenting today. It is ocean and it's a big journey, Imagine that, almost 40 odd students working for 5 years means 200 years of hard work, If you see, it's not easy, it's a lot of hard work. And then case 3, that is reduction of Indian network, which is also, though I said we have not published this work, never been published, but nevertheless, what I wanted to highlight is that uh, what exactly the Indian network happened to be in 2013. Why I have chosen 2013? Because that is the year the blackout occurred. And that is the year I wanted actually the DC microgrid is to cater electricity to the campus. Having a DC microgrid, my microgrid was not operational. So somewhere we missed it, but today we have the knowledge. We have controller mechanism where even if the grid is going out, still my DC microgrid can give some energy. Is it okay? So the Indian power system considered here corresponding to all India peak is on August 2013 with over 280,000 circuit kilometers of cables and 280,000 kilometers. India's transmission network is one of the largest network in the world. The whole network is divided into 5 zones, as we know, with buses at various voltage level. The actual Indian network considered here had 6,034 buses. Am I right? Out of which generators are connected to 575 buses and loads are connected to 3,400 buses. Connected by 8,116 lines. It is the story of 2013. In 2025, this figure might have gone 25% higher. So indirectly, the Indian system had 6,000 buses, and I have the capacity of 400 buses. So my target was to reduce from 600 to 400 buses, so that I can carry out real-time simulation in the laboratory. So the next generation is 120. The net generation at that time was 120 gigawatt. Okay, whereas the load was close to 117 gigawatt, and the losses were close to 2% before 13 years. So this is what we have done, the first PHIL. So what we have done, the reduced network had actually, we have reduced into 120 zones. I cannot reduce the buses directly. I can make clusters. The whole India can be divided into 120 zones with 216 lines only. So the network has been significantly reduced. So instead of saying no to a real-time analysis, so power hardware in loop simulation can be carried out for millions of microgrids for Indian grid is possible. But we need some smart reduction technique, smart simulation technique to achieve it. So what we have done actually, then we moved to feasibility study of DC microgrid integration to IIT Roorkee, because considering the challenges, we have reduced it, but then we realized, but it is not the exact one, okay? So we need to do something exact. So we have gone to IIT Roorkee distribution system, which has been developed. So slowly what I'm thinking in my Admire Desk lab, at the rate IIT.ITR.ac.in, I like to put IIT Roorkee network as it is, with all data. So that instead of playing with a 33 bus US system, you can also play an Indian system, because Roorkee means Jaipur, everything is reflective in India, okay? So you'll get into a sense and feeling of the Indian distribution system, and I expect everyone to simulate that in future. So we are working on that, and probably just note it down, you remind me, I'll try to put it in my website very soon, system data, okay, whatever we have developed. Practical IITR distribution is model in RTDS. Practical DC microgrid integration to IITR network is carried out. Significant improvement in bus voltage profile and effective utilization rooftop PV is observed. So having a microgrid with real-time operation, the voltage profile of the system can be easily operated. Optimal power flow of lines is also achieved by optimizing a placement of DC microgrids. So this is what actually the diagram you could see we have drawn in due course of time. But could you see the top one? It is IIT Roorkee sketch. So how we got that sketch? There was a paper lying for last 30, 40 years. We have taken a photograph of that sketch. And that is a mine distribution system. And then we simulated in the RTDS, the complete distribution system, right-hand side, okay? And then we have simulated very detailed. We could find runtime window for IIT Roorkee distribution system with DC microgrid using PHIL implementation. And then the last case study we have already seen. This is bus number, now let us take bus number 1 and bus number 22 and bus number 5. So 1, 5, 22. I think this also we simulated in real time. And last time we have seen simulation type, now it is PHIL exploitation. So this is the setup. We could see all the reactive power supplies. Could you see the real time one actually? There is a huge difference between your RTDS results and PHIL results. Am I right? Good. So mainly the presentation belongs to 3 IEEE transactions. Two, belongs to Sanjeev and 1 belongs to Guru Raj. So this IEEE transaction on smart grid and 2 belongs to industrial informatics. If you refer, probably you'll be able to understand all the CHIL and PHIL experimentation, including simulation and real time, both together. Okay. Good. So then we'll slowly move to system analysis of AC/DC microgrid. Okay. So why it is important AC/DC microgrid? Because as of now, we talked about a lab-based pilot where we have a single bus and we connect my DC load, I connect my AC load, I connect my DC generation, I connect my AC generation, everything is clubbed. But that is simply a laboratory experimentation, operation of microgrid. But if I go to the reality, the distance between my PV panel to my diesel generator, probably 300 meters. So there is a cable connected. So it is no more a bus, single bus, it is a system. It is a system. So when you talk about a system, so then you have AC to DC converters, DC to AC converters. So how do I carry out, for example, I have to sense a voltage. So the voltage solution will be available to me through a load flow, no? I cannot put devices, go there and measure it and come back. My system should give me different voltages, phases, currents. So in case of AC-DC hybrid microgrid, modeling of distribution system, having AC and DC microgrid become an interesting thing. Because let's say in this room, which is a AC grid, Prabha is a AC microgrid or DC microgrid? AC microgrid. It is a AC microgrid. Imagine from this plug, I have prepared a DC microgrid here. All right. And I like to simulate the AC microgrid along with the DC microgrid. And unfortunately, there is no conventional algorithm available. It is available today, but at that time it was not available, where you can simulate the AC system and DC system simultaneously. We all have learned HVDC systems, where AC bus and DC buses are connected. Am I right? But in a distribution system, AC DC distribution system load flow is not there in the textbook. So that is very interesting. So let's see how we are going to do it here. So AC DC distribution network, we are not talking about any test bed now, we are talking about system level AC DC microgrid, where structure of AC DC distribution network is important, classification of buses is important, overview of load flow analysis, AC DC load flow analysis and their challenges, power converter modelings, distributed generations modeling, basic steps for load flow formulation of AC DC distribution network. AC DC distribution networks, in the late 1880s, three exceptionally brilliant innovators, Nikola Tesla, George Westinghouse, and Thomas Edison, battled over which electricity system, whether AC or DC, is perfect. Okay? But due to numerous advantages of AC over DC, the latter was forced out of competition and AC emerged to be victorious. Owing to the ever increasing demand, declining conventional energy sources, and technology, revolution in deploying renewable energy sources, interest is invoked again on me and the world in the year 2013. 2013 में दोबारा people started thinking about DC as a sector. There are various advantages of DC over AC, but the complete reinforcement of existing distribution system into DC network is impractical and impossible. इतना दूर आगे अब वापस जाना मुश्किल है. It is something like snatching your mobile from you. It is next to impossible. So researchers are planning a hybrid distribution network. Instead of replacing AC by DC, let us have DC, let us have AC, and develop a hybrid algorithm to handle both AC and DC. So major component of AC-DC network, how it will look like, all of you please have a look. So if you see the, your orange color, they are all actually AC buses coming from a system. And then you are converting AC to DC. For example, the bus number 4 will be my DC and bus number 3 will be, okay. And then bus number 5 will be, bus number 23 will be, yes, DC-DC converter. And then you expand that microgrid. So what is happening? It is a AC system in which you have two major DC microgrids, and you also have from a DC grid to an AC microgrid also. For example, what is the bus number 16 is a DC bus below, and 17 is and then you create a AC microgrid. And this diagram has not been copied from any IEEE system. It has been created in the Admire lab itself. And this has been validated and rigorously being accepted by the world. Am I right? So all the systems, actually, I'm thinking slowly to put it in my Admire lab website so that you all can use it. If you're looking for AC system, you can have IIT Roorkee distribution system. If you're looking for AC/DC system, you can use such systems because you have already wasted time. I do not want others to waste time again and again. Okay? So the AC/DC distribution system consists of variety of AC and DC component, including loads, generating units, lines, and buses. In addition to traditional AC loads and AC generators, it can also include DC load such as EVs and DC sources such as PV panels. Renewable technologies, PV system, geothermal, wind generators, hydropower, etc. Now, if you see the type of buses, in AC system, we had three type of buses. One is PV bus, the other is PQ bus, and the third is slack bus. I hope you have not forgotten. So these are the three different type of buses in AC system: PV bus, PQ bus, and reference bus or slack bus. So what is PQ bus, where P and Q are known? What is PV bus, where P and V are known? What is slack bus, where V and theta are known? But if you go to a DC bus, you don't have Q there. You don't have theta there, So in a DC bus, there are two types of buses. One is DC load bus, where P is known, and you have a DC voltage control bus, where V is known. Okay, so this is how actually, because now you're moving slowly from AC system to a DC system, and how these algorithms can be used. So overview of a load flow analysis, where for proper planning, analysis, and optimal operation of transmission or distribution system, a power flow or load flow study has to be carried out. Load flow study is a steady state analysis whose target is to determine the voltage, current, and real and reactive power flows in a system under a given loading condition. The purpose of load flow studies is to plan ahead and account for various hypothetical situations. There are well-established algorithms for load flow solutions of AC/DC transmission system, example Gauss-Seidel, Newton-Raphson, fast decouple, and Broden methods. But owing to the high R by X ratio and mostly radial and weakly meshed structure of the AC/DC distribution system, the available load flow method for AC/DC transmission system cannot be applied to AC/DC distribution system. Why? Because the R by X ratio become very, very high. All right. So the Jacobian matrix that you see, which has only reactive components in transmission system, but in distribution system, it will be both real and reactive component. And that is very difficult for inversing a 100 by 100 matrix, which has both real and reactive parts. So the AC/DC distribution system is more complex than pure AC distribution system. It has many elements, renewable generations, converters whose input and output relations are non-linear. So AC/DC load flow analysis and challenges. Proper modeling of various types of power converters in the load flow equations. Modeling of various types of distributed generations, PV system, geothermal, wind generators, hydropower, they need to be modeled. Modeling of storage devices. This has never been taught to someone who is 45 years old today. For 20 years, we have been taught only very basics, thermal power plants, hydropower plants, no PV, no wind, nothing. Taking care of prerequisite control objective by the converters in the load flow equations. The load flow equations must be capable of modeling the operating state of the combined AC and DC systems under the specified conditions of load generation in AC/DC control strategies. So, for example, you had AC system, but now you are talking about AC-DC voltage source converter, VSC. So, this is how you have to model a VSC in case of system level analysis. You should not feel shocked or surprised. You have converters for your microgrid, but you must know in a line if the converter is connected, how to model. You know how to model line. You know, no. SPI and T model, no? Transmission. If it is distribution level, it is RLC. But if there is a converter in series of a line, you will be worried how to model it. You must know how to model the converter models. So the P, Q, voltages, angles, everything need to be calculated. Similarly, DC-DC converter model. You have a bus, DC-DC converter being connected. So if I'm interested to know the voltage at one end or angle at the other end, I must be in a position to determine. I cannot say I'm a polytronics man. I only know converter, not about angles and voltages. No, you must know it. Am I right? Then actually AC-DC line commuted converter modeling, and then distributed generation modeling with different types. All these types of DGs may be modeled in any one of these categories like PVDG, VDC-DG, PQ-DG, P-type DG, and so forth, because distributed generations are of many types. Okay, so what is type 1 modeling? This type of DG is capable of delivering only active power, such as photovoltaic. So I cannot model a PV DG with wind DG. Similarly, there are different elements. Similarly, type 2, where the DG capable of delivering both active and reactive. So a synchronous generator, a wind generator, they will fall under type 2. What is type 3? DG capable of delivering only reactive power. And type 4, DG capable of delivering active power but consuming reactive power. So one case delivering P, the other case P and Q, the third is only Q, the fourth is delivering P and consuming Q. So they need to be modeled differently. So what are the basic steps of load flow formulation of AC-DC distribution network? The mathematical model of both AC and DC distribution lines and cables is required. There should be proper mathematical modeling of various types of loads. You know how to model loads, okay? The most important part is modeling of various types of converters, taking care of the control objective that need to be achieved. Sir, where can I get to read? Read about how to? Read all my articles. That's enough. Okay. Yeah. Because I think the best way we describe in the laboratory, you take up one setup. The 3 articles that I given you, 2017 and I think 2017 articles, you take one article, any one of the article out of 3, because I give reference to each and every lecture. And read simply how the PHL experiment has been conducted. We have explained everything in steps very thoroughly. So the most important, thank you. So the most important part is modeling of various types of converters, taking care of the control objective that need to be achieved. Modeling of renewable generations, PV type, VDC, PQ type, P modeling is also required. The suitable unified sequential approach is required to stimulate all the mathematical models. And with this, we come to an end, because I'm not taking you deeper, because smart grid is a subject a single expert cannot neither handle nor teach. You have to be good at, power systems. You have to be good at polytronics, and you have to be also good at control, and you have to be good at actually hardware also. Okay, and bit of communication and cyber physical. So all these 6 MTech programs combined will make you a smart grid expert. All right, but whatever you need, you can be, specific to that area, and you can certainly achieve it. There is no doubt about it. So with this note, we come to an end. Thank you very much, and hope you all have enjoyed today's interaction. Thank you very much for your attention. Take care. Bye-bye. Any questions? I'll be happy to take a couple of them.
Any questions, please? You may chat box. We will make you panelist. You want to ask a question, please put in chat box. Which one is more complex?
Which one is more complex? What, AC microgrid, DC microgrid?
Hydro generator circuit.
I think both are same. Both are same. Different approach. PHAL is more complicated. Yeah. PHAL closed loop is complicated. Yeah.
Hydro generators are under which category of DG?
PV is directly connected to grid, and from grid supply is given to the house. How we can justify as grid? No, that's fine. Because if you do not, you see, when they connect the PV, not in Odisha, in most of the places across the country, the PV energy has been given to grid, and then they have been taken back to the residential areas. What is suggesting? We have a PV panel, even in my rooftop. I must use it. So most of the PV parks, they connect to the grid because the advantage actually you need not store them. If you connect to the grid is a hungry person. It will absorb all your energies. But if you connect not to the grid, then in the 7 o'clock, if your generation is peak and you are sleeping, then how do you store the energy? So you need a lot of a microgrid is required to utilize your own, or you need to reduce the PV generation to such a level that it will be consuming all the time. Even for a residential thing, it may so happen. Sometimes everything is off, you go for 3 days holiday, what will happen? So I think either you give to the grid or you have a control mechanism to optimize your renewable generations using batteries. Somebody asked actually, hydro generation falls under which type of PG? It is similar to your normal conventional generations only, but it's a renewable generation. It gives both P and Q to you.
सर आई थिंक उनका क्वेश्चन ऐसा था कि हमने सोलर पीवी लगा लिया और डायरेक्टली ग्रिड को फीड कर दिया ग्रिड तो डिस्टर्ब उनको नहीं पता है कि हम इतना इफेक्ट कर रहे हैं सब लोग करने लगे तो ग्रिड को इफेक्ट
nothing grid so big, grid is so big, this is like a very small element. It is not going to disturb your frequency. That's what we call grid as a infinite bus.
if all are used most of them
Even you do it, even if you do it, how much you will do? 1%, 0.5%, 2%. 50 hertz become actually 50.02. That's all. It is not going to collapse. I'm very happy today. So many questions bombarded. Okay, which one is not explored? AC or DC or AC/DC? All three are explored. All right, but few applications that need to be explored. Sir, which software was used for designing the model, MATLAB or PSCAD? Everything is RTDS here. RSCAD. Everything is RSCAD. So OpenLRT and RTDS do have their own softwares, but if you don't have, then you can use it PSCAD. Even you can use MATLAB for your learning stage, no issue. Next, please. And perhaps I told you, that the Indian grid has just been integrated to the RTDS. There actually we use MATLAB for reduction in the network, and then we integrated MATLAB to RSCAD. That also took years for us to learn. Yeah. Thank you. Okay, good. Excellent. Very nice talking. I'm very happy that, they're very active. Huh? Okay, take care. Thank you. Bye-bye for the day. Bye.
Thank you, sir. Okay, so thank you. We'll meet tomorrow. Next class. So only 3 classes.
It's a very informative session. Somebody's yeah, good. I think they're enjoying it.